Okay, does the mic work? Okay, so I'll be talking about agnostic private density estimation for Gaussian mixture models via list global stability. This is joint work with Mohammad Afzali and Hassan Ashtiani, both from McMaster. I'll mention that Mohammad was a master's student during this work, and he really drove this project. Okay, so what is density estimation? So the problem in density estimation is that there's some unknown distribution G. You're allowed to receive IID samples from it. You feed that into some algorithm, and the goal is to output some distribution F, which is ideally as close to G as possible. And just to make it a bit more formal, we usually assume that there is some class of distributions that we're trying to learn. And G is some unknown distribution might not be in this class of distributions that we're going to call F. And so given ID samples from G, we want to output a distribution that is within that class, satisfying one of two conditions. The easier condition is what's known as the realizable case, where we do assume that the unknown distribution is also part of that class. And here we want to get as close to it as possible, so within, say, total variation distance alpha. And the harder case that we're going to look at for this talk is known as the agnostic setting. Here we don't assume the distribution G is actually in that class. And so instead of getting within a constant within alpha, we're going to try to get within a constant factor of the best distribution, and then also add some alpha slack just in case it turns out to be very small. Okay, and so this talk will be on differential privacy as well. There's been 2 talks on this already, so I'll briefly go over this. So differential privacy just means that if I have 2 different data sets and I feed both of these into the same algorithm, then the output of the algorithm should be basically statistically indistinguishable, provided that the data sets are very similar. And we're going to focus on epsilon delta differential privacy in this talk. So the previous talk already gave you the definition, but here it is. So it's epsilon delta differentially private if for every event E, I look at the probability that the output of the algorithm given D is in E is upper bounded by something like E to the epsilon times the probability that the same event happens but under D prime, and then I add some fudge factor delta. And this is needed because for distribution learning, if you don't do epsilon delta differential privacy, then there's packing lower bounds that basically prove impossibility of results. Okay, so then our focus here is on private density estimation. So basically you put the 2 slides together. You have an unknown distribution, you feed these into an epsilon delta differential private algorithm, and you want to get something good out of it. And one thing I'll mention is that the privacy guarantee must hold for all inputs, even if they don't actually come from the distribution that you're trying to learn. But the utility guarantee only needs to hold when the inputs actually do come from the correct distribution. And there's a lot of exciting work on this just within the past few years. I'm probably missing a bunch of citations here. Okay, and just as a reminder what mixtures of Gaussians are, so Gaussians are parameterized by mean vector and a covariance matrix, and mixtures of Gaussians is just that you take a convex combination of them. If it's a mixture of K Gaussians, then you just take K convex combinations. Okay, so this is our main result of the paper. So what we show is that the class of mixtures of K Gaussians in D dimensions is epsilon delta privately and agnostically learnable. And in particular has some polynomial sample complexity. So something like K squared D to the 4, and then times some dependence on accuracy and privacy. This is likely not optimized, but it's the first polynomial result in the agnostic setting. And just as a reminder, so in the agnostic setting, we're trying to get a constant approximation to the best distribution in class. Here we get a 21 approximation, so this is likely not tight. And so an open question I'll mention here is that you can probably improve this constant. Another thing I want to mention is that even for the realizable setting, we didn't know how to do that until last year. And there's also been some progress on that since then. So for the realizable setting, the best bound is that's known as what's shown here. So something like KD squared plus K to 1.5 D to 1.75 plus K squared D. This was a work of one of my co-authors, with some of his co-authors in NeurIPS last year. So if you're interested in this, I encourage you to look at this paper. Okay, so probably for most of the remainder of the talk, I'll tell you a bit about how to prove such a theorem, and in particular is going to use some sort of reduction from distribution learning to basically designing lists globally stable learners, which turns out to be much simpler. And the idea of using these lists globally stable learners actually has appeared in the literature and has mostly been used for classification. And so to the best of my knowledge, this is the first time that it's been used for distribution learning. Okay, so I need to explain to you what list global stability is. So let's suppose I have a distribution class F. I'll say that an algorithm A is alpha accurate L list globally stable if for every distribution G, I can find some distribution F in my class that's allowed to depend on G, such that the following holds. You give me a sample set S that is actually drawn from G. What I want, first of all, is that the output of the algorithm is actually short. So it outputs a list of distributions, and it's not too long. So you have size of most L. And the second one is pretty important here. It's a stability guarantee. What I want to ensure is that with high probability over the samples given to me, the algorithm actually outputs this F here that I want it to, that I fix at the beginning of the statement. And of course, it has to be fairly accurate. So just to show this pictorially, I have some sample set S1. It outputs a list of stuff, and one of those elements I really want to contain F. I do that again. It might output a list of a bunch of different stuff, but in particular, it will output at least one distribution, which is still .F. And I do it again for S3, and it outputs again a list of different stuff, but importantly, F is still there. Okay, so that's list global stability. We also need to extend the agnostic setting. It's done in the most natural way. So it's alpha accurate agnostic L list globally stable if basically everything holds. The only difference is this total variation guarantee where we now just want it to be within a constant factor of the best distribution in class. Okay, so why do we care about list global stability? So we proved this theorem. What we show is that if a class of distributions F is alpha accurate agnostic L list globally stable, then it turns out that same class is also epsilon delta privately agnostic learnable, and it has sample complexity something like log squared L over delta over alpha squared epsilon. And so what this means is that in order to design in order to prove sample complexity bounds for learning a distribution, we just need to design these list globally stable learners, and the list size can be something like exponential in the parameters we care about. Okay, so explain how to do this reduction. So it's sort of a three-step process. So in the very first step, well, first of all, we draw samples from the distribution. And then what we're going to do is we're going to split the data set into T different sub-data sets, which I've drawn with different colors here. And then we have a list globally stable learner. And so what we're going to do is we're going to apply the globally stable learner on each of these partitions to get a list of candidates. Okay, so these red points got mapped to these red candidates. One of them contains F. For the orange one, we got unlucky. We didn't get the stable element. But for the purple one and the blue one, we also got the stable element. Okay, and the stable element is going to appear in almost all of these lists. So that's good. The second step here is that not all distributions here are actually going to be close to the true distribution. And so we'll just do some filtering step to ensure that basically the list only contains good elements. And intuitively that, oh yeah, one thing I'll mention here is that intuitively, the way you should think about it is that when we do this filtering step, definitely F, the stable element, or if there's other stable elements, those ones are going to probably survive this filtering step. Okay, so just a really high-level idea of how to do the filtering step. I'll say a little bit more in a bit. But the idea is that if we are in the realizable setting, for example, then we know that there's some distribution that's very, very close to the ground truth here that's denoted by star. So then we would like to draw a ball around that. And there's fairly standard tests. For example, you can look at the Roy Lugosi's book that will allow you to basically filter out all the points away from it and just keep the points close to it. Okay, so once you do the filtering step, you're basically left with a very simple task of choosing basically any element from one of the lists to output. So just note that nothing so far has been privatized, and that this really is the only privatization step in the whole algorithm. And so what we're going to use here is what's known as the choosing mechanism due to Bunn et al. And what the choosing mechanism says is that if we can define some suitable score function that's not too sensitive to the samples, then there's some mechanism that will allow us to output some high score element. And so a natural candidate to choose here, because we know that there is a stable element, is to just to find the score of every element that appears in the list. In all the list is basically the number of times that that element appears in the list, or the number of lists that contains that element. And so in particular, the stable element will appear in almost all the lists. And so definitely that is a candidate for a to be high score. And so basically, this allows us to actually output something that's fairly reasonable. Okay, so I do want to go back and mention one thing about the filtering step, which is that since we're in the agnostic setting, we actually don't know how close we might be to the ground truth a priori. And the main idea to get around this is to do some sort of binary search. So for example, we might start with this radius. Then we try to compute the high score elements, and we realize that there aren't any high score elements. So actually, in this case, the radius is too small. And so at a second step, we might increase the radius. Now we're getting a lot of high score elements. And so this gives us an upper bound on what the distance to the optimal ground truth is. And so the second step is then to decrease the radius, and then you just repeat this until the radius, until you're sufficiently confident in the radius that you need. Okay, so yeah, so that's basically the high-level idea of how to prove this reduction. And basically from here, in order to get a sample complexity bound for Gaussian mixture models, we just need a list decodable, list globally stable learner with sample complexities, with list size something like exponential and poly and D and K. Okay, so I'll just mention one other thing, which is that it turns out that if you want to design list globally stable learners for a mixture of distributions, you can actually just learn it for the base class instead. And this actually simplifies the problem a lot, because for example, for mixtures of Gaussians, now it just reduces to the single Gaussian problem. Okay, so at least for Gaussians, then all you have to do now is just to design a stable learner for Gaussians with size 2 to the poly D. So I'll just briefly go over that. So for this, it turns out that there is a result from 2020 due to myself and some co-authors, which actually give a list decodable learner for Gaussians. And the list size here is 2 to the poly D. But the issue with this is that it's not necessarily robust. If you analyze the proof, though, you'll notice that it outputs a lot of similar points, but they're not identical. And in order for us to use a reduction, we need them to be identical. And so you can just ask whether or not you can discretize this. To be honest, I don't know, because the covariance matrix, the geometry of that is kind of complicated. But it turns out what you can do is you can actually do a 1 to poly D discretization, 2 to poly D discretization. So instead of mapping one point to a discretized point, you actually map every point to 2 to the poly D discretized points. Okay, if you're familiar, this is known as locally small covers, and this is fine because if you increase the size by 2 to poly D, the total list size is still 2 to poly D. And so this construction for Gaussians basically allows you to prove sample complexity bounds for privately learning mixtures of Gaussians. Okay, so I'll just conclude here. So again, first result for agnostic learning mixtures of Gaussians. The constant here is 21, so an open question is to improve this constant, and also to improve the sample complexity here. And also we have a technique that we introduced for proving sample complexity bounds for density estimation based on list global stability. It would be interesting to see if we can apply this to other questions. Yeah, that's all I have.
Can you take one quick question? Do you think that like you have this log squared result in terms of like log squared L? I guess it would be really nice if you can reduce it to log L because that would give you an order D algorithm, right? Do you think that's possible, or does your framework not allow that? You think?
I have to look into it. I don't think we tried to optimize that hard, so it's maybe possible.
Okay.
That log square is often necessary for like replicability type things, and I think this will also lead to a replicable similar thing. So I would guess log squared is tight with that sort of technique.
Interesting. Okay. Maybe
So
we can talk about. Oh, sorry.
I'll just mention that the other result, the one that actually improves upon KD squared, that just moves a lot away from like replicability. So the replicability may also be like a bottleneck here. We need a different technique.
Cool. Thanks again, Chris.